Hello everybody. What I want to accomplish with this video is an introduction to some of the big things that are behind thermochemistry. Thermochemistry is really just the study or a look at how energy is related to chemical reactions. And we're not going to get too far into it. There's quite a bit more to thermochemistry than we're going to do. But just to get us started, a first look at sort of how energy can come and go during reactions and the different ways that we talk about that and some terms that go with it. And then we'll get into the numbers about how we calculate the amount of heat that's gained or lost by a reaction. So in thermochemistry, basic idea is this. All reactions like you've seen up until now, writing equations, predicting what will be formed by a reaction, even doing some stoichiometry, they all involve atoms, compounds, molecules, bonds being broken, bonds being formed. But they also involve the release or absorption of energy. And you see here I say net release and net absorption. All reactions overall either release more energy than you have to put in, that would be a net release of energy, or they absorb more energy than they release. So it takes more to make them happen than they release back at the end. But just to keep it simple, general idea is every reaction will either have an overall release of energy, a net release of energy, or a net absorption or input of energy. And you can see here on the left we have a flask reacting where the arrows to show the heat are being sort of released out from the flask's contents. And then at the bottom you see this in very small words, and we'll get into this more, the idea that would be an exothermic reaction. Now that's a term I know you've all heard before and are somewhat familiar with, but just to kind of bring it back and put it in front of you again with what we're doing here, exothermic on the left. And then on the right we have a reaction that's showing the arrows moving toward the flask, energy going into the flask and the reaction that's taking place in that flask. And then it's labeled there as endothermic below the flask. Notice that the labels in the flasks are kind of important too, that the contents on the left are hotter than their surroundings, and so heat would be released or transferred outward from the reaction in the flask to the surroundings. And on the right, the arrows are going toward the fact that in the flask, the reaction is taking place and the contents of the flask are cooler than their surroundings, which would allow heat or sort of almost force heat to be transferred into the flask. So imagine if you were holding these in your hand. If you're holding the flask on the left, you're going to feel heat coming out into your hand from the flask. And on the left, you're going to feel heat, or either on the right, you're going to feel heat transferring from your hand into the flask, and that's going to feel cool to you. Okay. So as you look at the pictures and as you look at the arrows, we're going to look at these again one at a time a bit more closely. Keep that in mind, to keep the perspective in mind as if this was happening in something that you were holding in your hands and how that would sort of be perceived by you and the sensation of that reaction happening in your hand. Let's look at that exothermic flask first. In the exothermic flask, again, there's a net release of energy. So it's giving off heat. It's giving off warmth, and we're going to feel that heat coming outward. To talk about sort of and explain in greater detail sort of how we put a number to that and sort of understand it as a quantity, then we want to think about that in this way. The amount of heat that's being released in an exothermic reaction is expressed as a number written in a negative amount, written as a negative amount. And you want to think about that because the reaction is losing energy. So because the reaction inside there is producing energy that's being lost to its surroundings, we show the heat transfer as a negative amount. Let me get a little bit closer look at that. If this flask is releasing energy, that's kind of like in this picture here. Someone on the top of the screen is handing money to someone on the bottom of the screen. If we see that money as sort of as a comparative to heat or energy, you can imagine the heat's being sort of sent outward from the person on the top. It's being sent outward or released by the person on the top. And so we sort of show the arrows leaving that person to show the direction of movement of the money, just like the direction of movement of energy would be outward from the flask. And if you're looking at that person there on the top who's spending all this money on their groceries, if you look at that person's bank balance while this happens, it might look like this. So if this graph is showing their bank balance over time, and this happens to have the months of the year across the bottom, but you get the idea. As we spend money, our bank balance would decrease, would drop. So if I start on this particular graph as an example, I start with $800, and over the course of time I go down to only $200. I've spent $600. And if I looked at my bank account over that time, it would show that as a minus $600, an outward spending of $600. Likewise, in a reaction that's exothermic and sends out energy, it's going to be shown as a release, a net release or loss of that 600 units of energy instead of $600. So when we see numbers written describing the energy associated with what's going on in a reaction, if it's an exothermic reaction that's releasing energy, it'll be shown as a negative value to show that the system, what's going on there in the flask, for example, is releasing or losing this amount of energy. So we show it again as a negative value. On the flip side, if we have an endothermic reaction, one that involves energy going inward more so than going outward, then in this case, on the flip side, if we have an endothermic reaction that's taking in more energy than it's putting out overall, we have a net absorption of energy. So heat energy is being taken in. And if I'm holding that in my hand again, that's going to feel cool. So the energy is moving inward toward the flask. And we show that inward movement of energy as a positive amount because the reaction system taking place in that flask or beaker or whatever it might be is gaining energy. And so likewise, we talked about with this money exchange, if I'm the person on the bottom of this picture and I'm receiving money as this process takes place, money's coming toward me, money's being absorbed kind of into my account as opposed to being released by the person on the top, then from where I'm standing, it's a gain of energy. It's an input of energy. It's an increase in my bank balance. So if I looked at my bank balance over time, maybe I'd start out, for example, with $300, and over time I gain and end up with $700. Then I would show that as a positive $400. I've increased my bank balance by $400. And likewise, if a reaction is taking in energy, we can put a number to that amount and show it as a positive amount if the reaction system is gaining and taking in energy. So, as we look at an endothermic reaction example, so here's an example of an endothermic reaction. We've got photosynthesis, and we know photosynthesis needs sunlight energy to make it happen. Plants need sunlight to produce sugar by photosynthesis. And so here's that reaction. Carbon dioxide and water are combined with energy from the sun to make glucose and oxygen gas, both of which, of course, are pretty important to us. We know this is an endothermic reaction because we know the sun needs to put energy into it, and we can actually look up the amount of energy needed for that. Energy coming into the system, coming into the photosynthesis happening in the chloroplasts of my cells in a plant, require 2,801 units of energy. Now, don't get too wrapped up in the unit kJ there. That stands for kilojoules. Kilojoules are a unit of energy like calories would be. They're actually a little different sort of style of unit than calories, but it's the idea of it's a heat unit. So don't worry too much about what a kilojoule is, but that it's a unit of energy, just like grams would be a unit of mass. And for this reaction, the amount of energy needed coming into to make this reaction happen is a gain of 2,801 kilojoules of energy for this reaction to happen. That little abbreviation that you see there in the front of this, delta H, a little triangle there, which is that Greek letter delta, which means change. We won't get into understanding or talking much about the details of what delta H naught, that little degree symbol, what that really means. But it, just for now, know that it's the symbol that we use in thermochemistry to show the amount of energy that's either being lost or, in this case, the amount of energy that's being gained by the reaction as it occurs. So this reaction has a gain, positive, 2,801 kilojoules for this reaction balanced as this equation shows. It's a lot of energy that gets stored in to make, in this case, sugar, 1 mole's worth of sugar from carbon dioxide and water and sunlight. So there's a lot of energy stored by photosynthesis. And we know that. That's kind of where all the energy gets started in our biopyramids in terms of energy stored in a biology or environmental science perspective. On the flip side, the last thing we want to think about with these endothermic reactions or any exothermic reactions, when we have that number, 2,801 kilojoules, what it's telling us is that we can relate that 2,801 to any one of the other participants in the reaction. This gives us a link between the carbon dioxide, the water, the C6H12O6, that's our sugar, and the oxygen. We have new ratios And when we have new ratios, we can use those in our stoichiometry. We've got all kinds of ratios that you've been using up to this point. 1 mole equals some number of grams equal to the molar mass. 1 mole equals 22.4 liters of gas. 1 mole equals 6.02 times 10 to the 23rd particles of something. And then we've had our molarity ratio as well. Here's another example of how we can relate heat energy to the substances involved in a reaction. 6 moles of carbon dioxide are linked then to 2,801 kilojoules. 6 moles of water are related to 2,801 kilojoules. 1 mole of sugar is related to 2,801 kilojoules, and 6 moles of oxygen as well. So you see we've got 4 new ways then to sort of fold energy into our understanding of this reaction. Not as a mole to mole ratio, but in sort of a similar way, a mole to kilojoule ratio based on this equation. And we'll work some problems out so you can sort of see how this gets worked into our math. I think you're going to make good sense of this rather quickly. Let's look at one exothermic reaction. Here's the equation for the formation of rust. So this is iron combining with oxygen to make iron oxide. And rusting is an exothermic process. It gives off heat. And so here's the reaction that happens when we look at one of these disposable sort of hand warmers that you tear the plastic open, a little cloth, kind of white cloth pouch usually, shake it up, and you put it in your glove or your pocket during a cold outside weather event, and it gets nice and warm in there for a while and gives off heat. And then when it's done, you throw it away. What's going on inside of that pouch is this reaction, the rusting of iron. And it's happening really quickly, so it's giving off heat very quickly, and you can actually feel it and take advantage of it to keep your hands warm. So as this reaction occurs, it gives off energy, specifically based on the equation as it's balanced here. 4 moles of iron plus 3 moles of oxygen gas make 2 moles of iron oxide, and it also releases 1,648 kilojoules of energy. So you can see the arrows sort of showing the energy being released from this system, and the negative sign on our value here showing us that it's a release of 1,648 kilojoules from the system. It's being lost by the atoms, by the bonds, and being released to the system outward. Okay. Again, we've got ratios as a result of that. 1,648 kilojoules can be related to 4 moles of iron. It can be related to 3 moles of oxygen. It can be related to 2 moles of iron oxide. Any of those, just like, as in stoichiometry, we could write a ratio of 4 moles of iron to every 3 moles of oxygen for a stoich calculation. We can do that with 4 moles of iron being across from or related to 1,648 kilojoules of energy being lost. So that's our ratio sort of process for how these problems will look. Let's work out a couple of problems to go along with this idea and show you how we work these into our calculations. Like I said, I think you're going to figure this out rather easily. Let's pick it up with that on the page that hopefully you have. And if you don't have a copy of the page, just copy down the problems as we go into your notes. We won't do too many in here, and I think you have a copy of this. So even if you do have to write it down, it won't be too much. So let's pick it up with the problems that should be on the page that you've received. And again, if you don't have a copy of this, just jot the question down. Take a minute to pause this and jot the question down in your notes. The problems aren't very long. So question number 1. When 2.31 grams of phosphorus reacts with gaseous chlorine gas to form phosphorus trichloride by the reaction shown below, what amount of heat is released to the surroundings? So we can see here we've got a general looking equation just like we've done for months and that we've looked at already with stoichiometry. And in fact, this question sort of almost sounds like a stoichiometry question that you've already done because it really sort of is. It's very much like those. But instead of asking, say, how much PCl3 will be made or how many liters of chlorine gas would be needed, this question wants to know how much heat is going to be released. If we start out with 2.31 grams of phosphorus, how much heat will be released? And so how do we know, first of all, that heat is being released? Well, it shows me over here that the delta H value, or that amount of heat, it's called the delta H, change in enthalpy, but delta H, change in H, it says here it's negative. So we know it's exothermic. It's a negative value, so I know it's exothermic. And I have a relationship to this reaction once it's been balanced. So as always, the first thing to do with our reaction equations here is to take a second to balance them. I'm going to have to go with a 3 and a 2 and a 2 to get this balanced. So once I've balanced that equation, I've got a connection between the phosphorus that I'm starting with here and the heat that's being released over here. And that connection that I've got is like a mole to mole ratio, except here it's a moles to kilojoules ratio. All right. Those two things put together tell me that for every 2 moles of phosphorus that react by this reaction, 641 kilojoules will be released. So for every 2 moles of phosphorus that I put in, 641 kilojoules will be released. And we keep the negative on there to show that it's a release or an exothermic reaction. So that's my ratio that might be valuable to me as I set this problem up and solve it. Let's go ahead and do that. As with all stoichiometry problems, we need to balance the equation first, and we did that. Now we're going to take our starting amount, which is our 2.31 grams of phosphorus, and we're going to convert to moles if we're not already there, and we're not. We usually aren't. So the first thing will be to convert to moles. So as always, 1 mole of phosphorus contains some number of grams of phosphorus. Nothing too different about this so far. We go to the periodic table, we look up phosphorus's mass. It's about 30.97 grams for every mole. And if I cancel my units off, like usual, I've got moles of phosphorus at this point in my problem. The question wants me to get it to heat. So now the question again becomes, do I have a relationship between moles of phosphorus, which are my current unit here, and heat? And I do. It's that important ratio that we started out with right over here earlier on when we first looked at the problem. We're going to go ahead and use that ratio in this box. But as always, let those units sort of set up how you structure your problem, how you organize your solution. I'm going to bring moles of phosphorus down here so that the units will cancel out. And again, I'm going to use this ratio that we came up with, which says that for every 2 moles of phosphorus, there will be a release of 641 kilojoules of energy. So I use that ratio, okay, that one that we got over here again, in here, in my stoichiometry, within my usual setup, in such a way that the units will cancel out. Moles of phosphorus will cancel out, and that'll leave me with kilojoules, which is our unit of energy, which is our amount of heat released. That's the unit that we'll see. So just like in a problem that we've done before, if it asked what mass of something is produced, you'd know that you need to be in grams. Or if it asked what volume of this gas would be produced, you'd need to be in liters. Likewise, what amount of heat is released needs to be in kilojoules or joules of energy. That kJ, remember, is our unit of energy. All right. So from here, it's just go to the calculator, punch it in, see what you come up with. And your calculator is going to spit out about negative 23.9 kilojoules. Remember, the units that you've got left here become the units that you have here. Okay? So we carry those across as always and make them our answer. So the answer here comes out of my calculation as negative 23.9. That means that 23.9 kilojoules of energy will be released. Now you might look at it and say, well, how come I don't write negative 23.9? The negative shows up in the word released. So if you're setting up the problem with an exothermic reaction, it'll come out as a negative answer because the delta H value that was given with the problem was negative. And so when I punch it in my calculator, it'll come out negative. But when we sort of speak that or express it or explain it to someone to show that we're releasing energy, we can show it as a negative, or we can say 23.9 kilojoules will be released, will be lost from the system. So there's our answer. 23.9 kilojoules will be released, or simply negative 23.9 is sort of the change in energy of this reaction. That's the setup. All right, let's try another one. All right, so this question says that when 1 mole of methane is burned at constant pressure, and we're not going to deal with anything changing pressures in any of these problems. It's a little bit more advanced than we need here. 890 kilojoules per mole of energy is released. So in this problem, we have 890 kilojoules of energy being released for every 1 mole of methane that comes out and comes into the reaction. That's sort of what that first sentence is saying. And it's released as heat. Calculate the heat released by a reaction in which 5.8 gram sample of CH4 is combusted. All right, so we need to balance our equation first. Let's take a minute to do that. So to balance this out, I'm going to need 2 in my waters to get those 4 hydrogens to balance out. 1 carbon on each side. That looks good. I have, let's see, on the right side I have 4 oxygen atoms, so I'm going to need a 2 over here in my oxygen, and then I should be balanced. So there's my balanced equation. When 1 mole of methane, it says, is burned, and there's 1 mole, 890 kilojoules of energy, it should probably be are released. And that's what I've got here. Okay? So that's my relationship. 1 mole of methane, CH4, is related to or is associated with the release of 890 kilojoules of energy. That's a ratio kind of like in the last problem. And the question says you're burning 5.8 grams of CH4. And they want to know how much heat's going to be released. So let's start it out. 5.8 grams of CH4. As always, if you're not in moles, you'll need to get to moles. So grams of CH4 will come down here and cancel out in my next step. And I'm trying to get to moles. Feel free to keep your little, if you've got a copy of the little mole ratios cheat card, all these different mole ratios on it, so you can find the one that you need. For example, here, this one, right? And all the others are still useful. They're all still fair game. In this packet, we see a lot of masses and stuff on this page, but they're all useful. 1 mole of CH4, go to my periodic table, 16.04 grams. That will allow my units of grams to cancel out and leave me with moles, which makes a lot of sense. And then I'm going to relate moles of CH4 to the heat energy that's linked to this reaction. And again, that's this ratio. We're going to have to flip it again because I want moles of CH4 to be down here. Got a little messy. And I want 890 kilojoules to be on the top. The release of 890 kilojoules of energy for every 1 mole of CH4. Again, that's simply coming from this one and this negative 890. Remember, when we get these values given, right, at the beginning of the question, you're provided with this information. This is for any part of the balanced equation. In this case, we're relating it to the CH4. In the last problem, we related it to the phosphorus. And it'll be different in each problem that we do. We'll relate it to different things in each problem that we write, in each one that we see. So go back to your calculation. Go back to your calculator. By this point, again, we've organized it so that our units will cancel out. And we'll punch it into our calculator and come up with an answer. And if you do, you'll get an answer of negative 320 kilojoules. Again, those units, kilojoules, are what was left at the end of my canceling. So that's the unit of my answer. And so calculate the heat released by a reaction. There again, the word released means we should see a negative sign with our answer, and we do. So you could write your answer as negative 320 kilojoules, or if you wanted to write it as more of a sentence or explain it a bit more, you would say 320 kilojoules of energy are being released. And we're usually going to be talking about heat as our energy. There's other types of energy. There's light energy, especially. I suppose even sound being released by a reaction, it takes energy, right? So you can write it as a sort of a sentence, or you can write it as a value. Again, the negative sign is the way we express the word released by our reaction, okay? Let's look at a reaction that takes energy in, a reaction that requires energy. So we can talk a little bit about how that looks, okay, in an equation where instead of releasing energy, energy is going to be required. Okay? Let's take a look at number 3. Now this is one that we already saw on the video, and I noticed that my value is a little bit different here. So I must have gotten my value from a different source when I wrote this question the first or second time. And so the little discrepancy in my 2802.5 here compared to what was in the video, let's not worry about that little glitch. I'll have to fix it for next time. But we've got an equation, and it was in the video, so maybe you remember it was balanced in such a way. But 6, 6, 1, and 6 are our coefficients on balancing that reaction. And this reaction, like we mentioned in the video, is endothermic. It needs energy. It needs quite a bit of energy. Energy from the sun is taken up by photosynthesis and incorporated into the sugar that's being produced, the glucose that photosynthesis results in, at least at the simplest levels. And so as we take it here, we're going to attack this problem using the ratios between water and the heat, or CO2, or sugar, or oxygen as the heat. Which part is this question asking about? Well, it says how much energy, so we are going to use our 2802 kilojoules, will be stored during the formation of 44 grams of sugar. And that's this guy right here, sugar. So we want to talk about 44 grams of C6H12O6. And you're welcome to just write the word sugar if you'd rather do that. We need to convert into moles. Grams of C6H12O6 are going to come in the bottom, so they'll cancel out. And I'm trying to get to my moles of sugar. So I know that for every 1 mole of sugar, there's a certain number of grams off my periodic table. You can go add it up and double check, but I think it's right around 180.2 grams. So I've converted my sugar that's being made, 44 grams. I think is about the amount in a can of Mountain Dew. I think that's why I picked this number. Okay. That's converted into moles, and then we're going to relate the 1 mole of our sugar to our delta H value, our heat being required or heat being absorbed. A gain of 2,802.5 kilojoules for every 1 mole of sugar that you make. Right? And again, our units cancel out nicely because of how we organized our problem. And we'll be able to go to our calculator and punch this in. Go ahead and do that. You should get an answer somewhere in the neighborhood of about 680. It's a positive value this time, 680 kilojoules. Now, if your rounding is a little different than mine, I am rounding by our rules of rounding for chemistry. And so if you're getting a little different answers and it's not exactly 680, just know that I'm rounding based on the rules that I haven't maybe hammered into your head enough yet that you just automatically do it too. But hopefully your answer is in the vicinity of 680. And so the positive answer, the positive sign on my answer means that it is a gain of energy. It's a storing of energy in the bonds of the sugar molecule. That's kind of the notion. And so as we put this reaction together to produce enough sugar to make your 1 can of Mountain Dew, plants had to somewhere take in 680 kilojoules worth of sunlight energy in the process of doing that. So that's our answer. Positive 680 kilojoules would be needed. Okay, let's look at another one. We'll do one more here. Make sure that I'm going to pick the right one to get us underway. Tell you what, let's jump all the way to number 8 and set this one up so that we start out with a little different look. All right. Plus, it's got a little trivial conversion in it that you haven't heard about yet. But it's a conversion that you'd be familiar with from your metric system days way back in grade school. This question says, what mass of ozone, and there's ozone's formula is O3, can be produced according to the reaction below, given excess oxygen. So we've got all kinds of oxygen in our atmosphere, and that oxygen is every day being converted into ozone gas. One place that it happens very naturally and all the time is in lightning strikes. So if you see lightning strikes, or if you're near lightning strikes during a thunderstorm, if you know the smell of ozone, you might actually smell it. Another place you can sometimes smell ozone is around like electrical boxes, especially large, high-voltage electrical boxes that are out and about in neighborhoods sometimes, those green boxes that you find in people's backyards. There's a lot of electricity kind of going through those for the houses of that area. And sometimes near those boxes, you'll catch a little whiff of ozone. It's not very good for you, though, so you shouldn't be around it. And thankfully, it dissipates into our atmosphere and doesn't build up. But you wouldn't want to be around ozone for very long. It's a pretty aggressive gas. But here's how it's made. Oxygen molecules are converted into ozone molecules. Well, O2 is not the same as O3, so we should balance that equation. It takes 3 oxygen molecules to make 2 ozone molecules. Really simple looking equation, right? But it's an endothermic reaction. It needs energy, and that makes sense because lightning bolts would provide that energy, for example. And so to make ozone takes, according to this, an addition of 285.4 kilojoules for every 2 moles of ozone gas that are produced from 3 moles of oxygen gas. That's what this is telling us. It's asking how much ozone or what mass of ozone can be produced according to the reaction by adding 425,000 joules of heat. Now, a joule is not a kilojoule. So one thing we should do right away here is get those units to match up. 425,000 joules is kind of like a conversion from grams to kilograms. It's a factor of 1,000. So just a sort of sidebar here, just like we've done 1,000 to 1 for like milliliters and liters, the same idea here. 1 kilojoule is equal to 1,000 joules. So before we get started, maybe it wouldn't be a bad idea just for us to convert that. That's 425 kilojoules of energy that we have available. So that's how much we're putting in, 425 kilojoules of heat energy being supplied. And now they want to know how much ozone we can make. Well, let's take that 425 kilojoules and go for it. All right, let's solve it. Take that answer and run. Do we have a way to connect kilojoules of energy to moles of ozone gas? We do. It's right here. It's a 285.4 kilojoules. 285.4 kilojoules for every 2 moles of ozone gas being made. So there's our ratio from the balanced equation. A little different than the ones we've done up to this point because we're starting the problem with energy instead of starting it with grams of something and then having to kind of get to that later on. But we're not quite done. All right, the question wants mass of ozone, and of course that's going to be in grams. We need to get ozone into grams. So we need one more step, and we need to convert O3, moles of O3, into grams of O3. And then for grams and moles, we go back to our periodic table and get that molar mass. 1 mole of ozone is around 48 grams of oxygen. And then we're done. Our units should cancel out. Kilojoules cancel. Moles of ozone cancel. And we'll have an answer at the end. Okay. Comes out to be somewhere around 143 grams of ozone that will be produced. So that's kind of how we can do a basic thermochemistry calculation given some other quantity to start with to find heat that's being released or absorbed, or, as you saw in this last one, a certain amount of heat, and determining then how much you can do with that heat. How much ozone can you make with that heat energy that's available? That's a nice cross-section of these. Take a look at the others. See if you can't get those answers to work out. I'll take a quick moment here and just jot the answers down for you on the remaining problems if you want to just put these in the margins, and then you can check them as you go. All right. So the answer that you should come up with on number 4, if everything goes according to plan, should be in the neighborhood of about 21,200 joules. Notice we're working in joules in that one. In fact, they even gave us joules as the delta H value for the reaction. On number 5, you should get an answer of actually, I might have you hold off with number 5. Okay, for now, I'll come back to that. Number 6, we're going to get an answer of 523 kilojoules. Or in the end, it'll actually show up as a negative 523. And then on number 7, it should show up as a negative 142 kilojoules. All right, now what about number 5? Just kind of a little hint, and I won't work it out with you, but I'm going to have you sort of look at this one as the first example of the last thing we'll talk about in stoichiometry, which is coming up next week, I think. That if you haven't already learned about limiting and excess reactants, this problem is going to introduce us to it a little bit. But I'll give you this much of a hint. And number 5, you're actually going to have to do 2 separate calculations. You're going to have to do a calculation that starts out with 65.50 liters of hydrogen. And you see that there in the problem. And then a separate calculation that starts out with 500 grams of iodine. And at the end of both of those calculations, you'll have an answer in kilojoules. You'll end up with 2 answers then, right? Way over here, you'll end up with an answer coming from each of those problems as you calculate things out. And if you set everything up right there, you should get 2 different answers. Okay? We'll talk more about how you decide which of those answers is correct. The short answer is it's the smaller of the 2 answers that ends up being correct. And we'll get more into the reasons why if you haven't heard about those already. But the smaller of the 2 answers that you come up with, it should be 104.3 kilojoules. And then the other answer that you come up with should be 154.9 kilojoules. So those are your 2 answers. It turns out this one is going to be the better of the 2 answers, the correct of the 2 answers. But those are the 2 answers that you need to be able to get from your math and work in those questions. Take the time that you need to work through the rest of these. Good luck with them, and I will talk to you when I see you.